Exercise 19. Prove the category equivalence between the category of functors from C to D. So see there are two categories, and then you take the opposite category. It's isomorphic to, it's category equivalent to the category of functors from C up to D up. So let's fix some notation to be used in the proof, because we're talking about opposite categories. These symbols could be very easy to lost. So let's say that if you took an object from category C, then it corresponds to object in its opposite category. Basically, it's the same object, but let's give it a different notation, which means that this helps us to know where it lies in. When we say X up, we know, okay, this is X, but in the category C up. Similarly, if we have homomorphism F in the category C, denote its corresponding homomorphism by F up from Y up to X up, and we know this is in C up. So more precisely, this means that take any morphism from the home, take any element from the home set from X to Y in category C. We know there is bijection to the home set in C up, but from Y to X. So use our notation just introduced, and let's write Y up to X up. So which means this F up is the one identifies with F, or is the one who is in 1-to-Y correspondence with F. We denote it by F up. Okay, so let's start the solution. What we do is we're going to construct a functor from this category to this category. So because this is category of functors, so objects would be functor itself, and morphisms would be natural transformations of functors. This makes things very easy to get lost. That's why we introduced the notations. Okay, so I would prefer to also write down this category of functors from C to D, because there is a relation with this category of its op, which means this helped me to know what's happening. I could always translate what's happened there back to there, right? In particular, so let's start with taking an object. So let me simply write this. Let's start with a functor in this category. Let's denote it by F. And so we're going to use this to construct a functor which is called alpha of F. Okay. So this alpha of F, we have to define it as a functor, which means you have to define it in the level of object and define the level of morphism. and basically we will define this functor alpha. We're also doing this thing in the level of object and in the level of morphism. Okay, so actually we should write f op, but when this is just in the level of object, we know they are the same. Void we using op, we just write f. And we're talking about morphism, we should be more careful. Okay, so as object, let's take any object x c op. So let's use our notation to call it x op. To remember it's c op. And so we have to define what's its image. What we know is that we're going to use the information on this side, construct the information here, right? So what we have is we have this functor f. So in particular we have this fx, which is in D, and so the op of fx is in D op. So basically it still maps x to fx. Okay, and then the level morphism, suppose we have arbitrary morphism x op to y op, call this f op, and then it's mapped to alpha f x op, which is by our construction of alpha f, this is just fx op, right? And then because we're talking about functor, we're talking about just functors, always we mean contrariant functor, unless it's mentioned. It's always covariant unless we mention it's contrariant. Okay, so just keep the direction, and so here is alpha f y op. So this is f y op. And so now we have to define what is this alpha of f op. What we do is we have to use the known information. We have fx op, fy op. What we know is that firstly this is in C op, but this has bijection with what happens in C, y to x in C. This is the same. Their home set are the same, so there is one element in that home set bijection with this home canonical bijection. Okay, and so in particular, by applying functor f, we have f of y, again covariant, f of x, because f is just a functor from C to D. So this is in D. F is just an element in this category of functors, okay, as object of this category. So f in this category is the same as f op. I mean things become different only when we talk about morphism. But this is just an object, so f is also just a covariant functor. Don't have to worry about that. Although there is op here, I mean, you don't have to care about the objects. The objects here are the same as the objects in functors from C to D, so they're covariant functors. So we got this ff from fy to fx, and so here it's in the op by that bijection relation. This tells us we could define reasonable map from fx op to fy op. So this would be just f and then op, which means this is how we define our alpha f of f op. We define to be this one. This is our definition. Okay, and so we have defined this functor alpha in the level of object. Now we have to define in the level of morphism. What we do is, the level of morphism, this is natural transformations from f to some g. Let's call this theta. Here we should be careful. Let's use the notation before. We should be careful, use the notation op, because as I said, in the level of object it's the same, so I will not bother to write f op, I will just write f. Okay, but this theta op, let's keep this theta op to remember. This is in the opposite category, and so we're going to define what is image of alpha for this morphism, which should be alpha of f, and then alpha of theta op, and then alpha of g. Okay, so how do we define this natural transformation? What we have is, let's first translate what we know. What we have is this map from f to g in the opposite category. This is bijective to the home set from f to g is bijective to the home set of g to f. In the category of functors. Let me write like this. G to f. So this is in to D, and this is in functor should do D op. Okay. And so if we write this as a commutative diagram, which means that for any x to y f, let's say we have g of x, theta x, f of x, g of y. These are again all covariant functors, f of y, theta of y. Commutative diagram for any x to yf. Okay, this is in D. And so this corresponds to g of x, theta op of x, fx. More precisely, this should be g of x, f of x, but as I said, as object they're the same, so I don't want to bother is writing up there, but this theta is morphism of the category, so in the opposite category should change the direction. So we have to change it. And this is also in D. Okay? And now for our map of functors of natural transformations between alpha f and alpha g. What we do is you have to start with arbitrary morphism in C-op. So you take to be compatible with the information we got. So let's take x up, f up, y up. This is in C up. Okay? And then to check this is a natural transformation, or I have to construct what it is alpha of theta up to make diagram commutes. So we have to apply alpha f on x up. I just write down this one, and because we know what it is, this is by our construction here, this is just fx up. So let me just write down this, and so then what we have is we have to define what is this theta to gx up, and then again they are just covariant functors. Still preserve the directions, so fy up, gy up. It's left to define what are these horizontal maps. So this is just alpha f of f up, which is just ff up, gf up. Okay, we're going to define this horizontal one, so this is theta alpha theta up x. We're going to define this such that make the diagram commutes to be just to be the one which has bijection with this. We have gx to fx. We're just going to define this as theta x up, which means because all what happened here is in d up, which means this is morphisms in d, and it has bijection with morphisms in d up. With that bijection, this diagram corresponds to a diagram here, and so this I would define to be theta y up. And so this tells us that this is, by the definition just given, this is natural transformation. Actually, this is theta up, right? And so we have constructed this map of categories. I construct this functor alpha in the level of object and in the level of morphism. What I left to check is to check this is the category equivalence. So essentially surjective. And check that fully faithful. the sensor's reactivity is obvious. Whatever functor from C up to D up, it is an image of some functor here from C to D, in the opposite category of the functor from C to D. Basically, whatever functor you have here, just define this. It's just the image of the functor, the same as f. Secondly, to say the fully faithfulness, it's also not difficult. Basically, we already say that, almost say that in this level, natural transformations. Basically, what you have to check is home functor C to D up F to G bijective to home set functor C up D up alpha F alpha G. That's what you have to check. By our construction, so natural transformation from F to G, natural transformations from F to G bijective is natural transformations from alpha F to alpha G.